Good morning everyone. I Vanshaj from Basic Chemistry Honours 3rd year. In this session of audio lecture for visually impaired students, I have prepared a audio lecture on the topic electromagnetic spectrum, absorption spectra, ultraviolet spectroscopy, which was taken from the book Pradeep's Organic Chemistry Volume 3rd, written by Dr. S.N. Dhawan. Now let's start electromagnetic spectrum absorption spectra 1 ultraviolet spectroscopy. First 1.1 introduction. One of the most important areas of interest of an organic chemist is to determine the structure of organic compound whether isolated from natural sources or prepared in the laboratory. The procedure generally employed consisting of the following steps: purification, detection and estimation of elements, determination of molecular mass, calculation of the molecular formula, determination of the structure. Till recently, the structure of the organic compounds were mainly determined through their chemical reactions, degradation, and chemical synthesis. This process is quite tedious and time consuming. However, during the last 3 decades, a large number of physical methods have been developed which served as powerful tools for the determination of structure of organic compound. Of these, the most commonly used methods are the spectroscopic method such as ultraviolet, infrared, nuclear magnetic resonance spectroscopy and mass spectrometry. The molecular mass and molecular formula can be determined by the use of mass spectrometry. The nature of the functional groups present in an organic compound can be determined by a combination of UV and IR spectroscopies. The complete structure, including the stereochemistry of the organic compound, is then determined by the use of NMR spectroscopy. These spectroscopic methods of structure elucidation are preferred over the classical method because of the following advantages. These require only a small amount of the organic compound. These methods require a much smaller time and the information is obtained on a chart which serves as the permanent record. Third one, during most of the spectroscopic studies, expect mass spectrometry, the compound remains unaffected chemically and hence can be recovered. Most of these methods are extremely sensitive to small changes in a spatial orientation of the various atoms present in a molecule and hence are generally used to determine the stereochemistry of the organic compounds. Fifth one, these methods are also useful for determining the mechanism and rates of chemical reaction. In this chapter, we shall discuss the basic principle and application of some of the most commonly used spectroscopic methods in organic chemistry. Electromagnetic radiations. Visible light is a form of energy which can be described by two complementary theories, that is corpuscular theory and wave theory. Neither of these two theories can explain all the properties of light. Some property of light such as photochemical effect, black body radiation can be explained only by the corpuscular theory, while other properties of light such as diffraction, interference, etc., can be explained only by the wave theory. In this chapter, we are only concerned with the wave nature of light, which is briefly discussed below. 1.2.1 Electromagnetic Wave Theory. Wave theory of light was put forward by James Clerk Maxwell in 1864. According to this theory, energy is emitted from any source such as heated rod or tungsten filament of electric bulb continuously in form of waves or radiations, and the energy thus emitted is called the radiant energy. The most example of radiant energy are heat, light, X-rays, gamma rays, etc. Second one, each radiation consists of mutually perpendicular oscillating electric and magnetic fields, both of which are perpendicular to the direction of propagation of the radiation. In other words, radiations are associated with both electric and magnetic fields and hence are called electromagnetic radiations. Third one, all radiation have wave character and travel with the velocity of light 3 into 10 power 10 centimeters per second. Some important characteristics of electromagnetic radiations. First, wavelength. It is defined as the distance between two consecutive crests or troughs. It is generally represented by the Greek letter lambda and is expressed in number of units such as angstrom, micron, millicron and nanometer. Second, frequency. It is defined as the number of waves which pass through a given point in 1 second. It is represented by the Greek letter nu and is expressed in terms of cycles, second or hertz or simply as second per third, velocity. The linear distance which a wave travels in 1 second is called its velocity. It is represented by the letter c and is expressed in centimeter per second or meter per second. Fourth, wave number. It is defined as the number of waves present in 1 centimeter length or simply the reciprocal of the wavelength. It is usually represented by the symbol nu dash. Thus, nu dash is equal to 1 by lambda. Obviously, unit of nu will be centimeter per second if nu is expressed in centimeter or per meter. If gamma is expressed in meter, further since C equals to nu gamma or lambda equal to C by V, nu equal to V into by C. The field of spectroscopy deals with the study of absorption or emission of the electromagnetic radiations. We are familiar with a number of different types of electromagnetic radiations such as cosmic rays, gamma rays, X rays, ultraviolet light, visible light, infrared rays, microwaves, radio waves, radar waves, etc. All these radiation travel with the same velocity, that is 3 into 10 about 10 centimeter per second, but differ from one another in the wavelength or frequency of their waves. The arrangement of all types of electromagnetic radiations in the order of increasing wavelength or decreasing frequency is called the electromagnetic spectrum. The complete electromagnetic spectrum is shown in figure 1.1. What is spectroscopy? Spectroscopy may be defined as the interaction of matter with electromagnetic radiation so that energy is absorbed or emitted in accordance with the relation delta E equals to h nu, where h is called the Planck constant and nu is the frequency of radiation and delta E is the energy difference between the initial and final state of matter. Now, types of spectroscopies. The field of spectroscopy can be broadly divided into two categories. First, emission spectroscopy. Second, absorption spectroscopy. Emission spectroscopy. When atoms or molecules are subjected to intense heat or an electric discharge, they absorb energy and get excited. During this excitation, the electrons in the ground state of the atom or the molecule are excited to some higher energy state. Since the lifetimes of these excited state is short, so they return to some lower excited state or ground state and the absorbed energy is released as light. When this emitted radiation is passed through a prism, it gives rise to an emission spectrum. In case of atom, such a spectrum recorded on a photographic plate commonly appears as bright line up to the dark background, whereas molecules give rise to bands. Now, second, absorption spectroscopy. If electromagnetic radiation is allowed to pass through a transparent medium, some is reflected, some is absorbed, and the remainder transmitted. When transmitted light is passed through a prism or grating, an absorption spectrum is obtained. This spectrum indicates those portions of the incident light that have been absorbed by the medium. For example, when sodium flame is examined by a spectroscope, it reveals the presence of two yellow lines called D1 and D2 corresponding to wavelength 5890 and 5896 angstrom respectively. These two yellow lines constitute the emission spectrum of sodium. However, when the same sodium flame is placed in the path of an arc light, the spectroscope reveals the presence of all the spectral lines of white light except for the two lines corresponding to the wavelengths D1 and D2, which are now found missing, and two dark lines appear in their place. These two dark lines constitute the absorption spectrum of sodium. Whereas emission spectroscopy is useful for the study of atoms, absorption spectroscopy is generally used for the determination of structure of organic compounds. This is due to the reason that most of the organic compounds are not stable under the drastic conditions necessary to record an emission spectrum. Therefore, in this unit, we shall discuss only the absorption spectroscopy. Now, absorption spectroscopy. Depending upon the type of electromagnetic radiation absorbed, the field of absorption spectroscopy can be divided into the following types: ultraviolet and visible spectroscopy, infrared spectroscopy, microwave, nuclear magnetic resonance spectroscopy, electron spin resonance spectroscopy. Now, unit used in various absorption spectroscopies. The users of different spectroscopies techniques use different unit of measurement of wavelength. In the ultraviolet and visible spectroscopy, the unit of measurement of wavelength is millimicrons or nanometers. In the infrared spectroscopy, the unit of measurement are the microns or micrometers or wave numbers, that is reciprocal wavelength or number of waves per centimeter. In the NMR spectroscopy, the radio waves used are defined not in terms of wavelength but in terms of frequency, cycle per second or hertz. In the NMR region, the radio waves used have frequency in the megacycle per second region. Let us now discuss various aspects of UV spectroscopy in some detail. Ultraviolet and visible spectroscopy. The UV region of the electromagnetic spectrum extends from 100 to 400 nanometer, while the visible region extends from 400 to 800 nanometer. The UV region is further divided into two separate regions, that extending from 100 to 200 nanometer is called the far UV region, while that extended from 200 to 400 nanometer is called near UV region. The subdivision is necessary for practical reason. At or below 200 nanometer, O2 absorbs strongly, therefore measurement in this region are done by flushing the instrument with nitrogen. However, at 150 nanometer or below, N2 starts absorbing. Therefore, the region below 150 nanometer can be studied only by using evacuated instruments. That is why the region below 150 nanometer is called the vacuum region. Now, principle. When UV or visible radiation is passed through the solution of an organic compound, it is either observed or transmitted depending upon its wavelength and the molecular structure of the organic compound. As a result of the absorption of energy, an electron gets excited from the ground electronic state to some higher electronic state. During this absorption process, some of the molecule of the organic compound will collide with the photon of the radiant energy. Although a large number of such proton molecule collisions are possible, but only those will result in absorption of the energy in which the energy of the photon exactly matches the difference in energy of the electron in the ground and the electronic states of the molecules as shown in figure 1.3. If E0 and E1 are the energy of the ground and first excited electronic state of the molecule respectively, and delta is the difference in energy between two states, then delta E equals to E1 minus E0 equals to H nu equals to Hc by lambda, where the letters Hc, lambda and nu have their usual meanings, or energy per absorbed per mole Na Hc upon lambda, where Na is the Avogadro number. Substituting these value of constant, we get the energy absorbed per mole. Thus, if the UV radiation used has a wavelength of 286 nanometer, it corresponds to an energy of 4.18 into 10 to the power 5 joule per mole. This much amount of energy is sufficient to bring about a chemical change. That is why photochemical reactions are usually carried out with UV or visible radiation. Thus, absorption of energy in UV or visible region occurs due to transition between electronic energy levels within the molecule. That is why UV spectroscopy is called electronic spectroscopy. Laws of absorption. The absorption of radiant energy by molecules is governed by following two laws. Beer's law. It states that the amount of light absorbed is proportional to the concentration of the absorbing solute or to the number of the absorbing molecule present in a medium, and that each molecule absorbs the same fraction of incident light regardless of the concentration. Now, second Lambert's law. It said that the fraction of the light absorbed by a homogeneous medium is independent of the intensity of the incident light, and that each successive unit layer of the medium absorbs an equal fraction of light incident upon it. Combining these two laws, the following empirical expression called the Beers-Lambert's law may be formulated as law I naught by I equals to epsilon Ci equals to A, where I naught equals to intensity of incident light, I equals to intensity of transmitted light, C equals to concentration of solution in moles. C equals to concentration of the solution in moles per liter. L equals to path length of the sample, usually 1 centimeter. Epsilon naught molar absorptivity or molar extinction coefficient. A equals to absorbance or optical density and usually has value between 0 to 2. Limitations. The Beers-Lambert's law is rigorously obeyed when a single species gives the observed absorption. However, the law is not obeyed when first different forms of the absorbing molecule are in equilibrium, for example, keto-enol tautomers. Second, solute and solvent form complexes through some sort of association. There is a thermal equilibrium between ground electronic state and a low lying excited state. Fourth, fluorescent compounds or the compounds changed by irradiation are present. Now, molar absorptivity. Molar absorptivity, formerly known as molar excitation coefficient, is a property of the molecule undergoing an electronic transition. Its magnitude depends upon the probability of that transition and the size of absorbing system chromophore. The typical values of molar absorptivity vary from 0 to 10 raised to power 6. Values above 10 raised to power 4 are termed a high intensity absorption, while values below 10 raised to power 3 are called low intensity absorption. Forbidden transition have absorptivity in the range 0 to 1000. Thus, molar absorptivity has a units of 1000 centimeters square per mole and or area mole, but these units by convention are never used. Instrument usually UV visible spectrometer. An instrument used to measure the percentage of the radiation absorbed or emitted when a radiation of certain intensity and wavelength range is passed through the sample of an organic compound is called a spectrophotometer or spectrometer. The modern ultraviolet visible spectrometer consists of a radiation source, a monochromator, a detector or an amplifier, and some recording device as shown in figure 1.4. The most suitable source of light in the UV region is the hydrogen and deuterium discharge lamp, while a tungsten filament lamp is used for the visible region. Most of the spectrometers are double beam instruments, thus electromagnetic radiation from the light source are made to fall on a rotating quartz prism to get a continuum of wavelengths, which are then separated into radiation of individual wavelengths with the help of a number of quartz slits. The monochromatic light thus obtained is split into two beams, one of which passes through the sample dissolved in a transparent solvent and other through the solvent. The intensity of each emergent beam is measured with photocells, and then the instrument electronically subtracts the absorption due to the solvent from the absorption due to the sample. The resultant intensity signal is automatically recorded on a graph as a function of wavelength. This recording of the percentage of the radiation absorbed or transmitted is called the absorption spectrum. Band nature of UV spectrum. A UV visible absorption spectrum consists of a few absorption bands rather than sharp peak as explained below. Absorption in the UV and visible region occurs due to electronic transition which require a large amount of energy, while lesser amount of energy is needed for vibrational transition and still lesser for rotational transition. In molecules, there are only a few electronic states. Each electronic state is associated with a number of closely spaced vibrational substates, and each vibrational state in turn has a series of closely spaced rotational level. In principle, electronic excitation can occur from any vibrational sublevel of the ground electronic state, but these generally occur from mu0 level of the ground electronic state because it is the most highly populated state of the molecules at room temperature. As a result of these transitions, the absorption spectrum of the molecule in the vapor phase would contain a large number of closely spaced lines which can only be separated with instruments of high resolutions. Further, even in the vapor phase, the ordinary laboratory measurement cannot make distinction between these discrete lines and hence record broad absorption band as a result of coalescing of absorption lines. Thus, UV and visible spectra of organic molecule consist of bands rather than peaks. Presentation of spectral data. Thus, the ultraviolet visible spectrum is generally recorded as a plot of absorbance versus wavelength. It is customary to then replot the data with epsilon or log epsilon plotted on the ordinate and the wavelength in the nanometer or millimicrons as abscissa. Since the values of molar extinction coefficient vary from 10 to 10 raised to power 6, it is customary to plot log epsilon as ordinate against wavelength as abscissa. The UV or visible spectrum usually consists of one or more spectrum band. The position of each absorption band is indicated by lambda max or epsilon max, where epsilon max is the wavelength corresponding to the top of the absorption band and epsilon max is the intensity of the absorption at this point. For example, the UV spectrum of acetone in hexane is shown in figure 1.6. However, if the molecular mass of the organic compound is not known, its epsilon or log epsilon cannot be calculated. In such cases, the intensity of absorption is expressed as A, that is, as absorption of 1% solution of the compound in a cell of 1 centimeter path length. This is all from my side. Thank you and have a nice day.